I'm going to talk of this model that with Professor Citti and Professor Sarti we elaborated about the a possible reconstruction which is happening in the first cortical layer, also called V1 cortex. So this will be the flow of my expose. First, I will recall how the action of the receptive profiles in the visual cortex behaves. Then I will introduce our heterogeneous Poisson's kind equation, and then I will show some numerical implementation. And finally, we thought that the qualitative results that we obtain are pretty good, but we don't have a complete understanding of the situation yet. So we started a theoretical analysis of what is going on in our model. So through some discretization and homogenization procedures, I will show why we think this implementation method works well. So first of all, in the first layer of the visual cortex, we have a distribution of receptive profiles that act on the retinal input and through a convolution procedure, and we obtain after this convolution a cortical output. So the function E defined on the retinal plane is a function that we can imagine from R2 to an interval such as 0, 1 if the image is black and white. Clearly we need more channels if the image is colored. And we have this action of the receptive profiles, a convolution action that gives the output function on the cortical level. Example of these receptive profiles for the so-called Mexican hat receptive profile, which is diffused in the rodents, is the Laplacian of a Gaussian function, and so the action is the convolution of the Laplacian of the Gaussian with the retinal input. I will explain what is E sigma in a moment. Then we have primate cells, simple cells. The receptive profile there is a directional derivative of degree 2, always of a Gaussian function, and here we have the output. E sigma is nothing more than a smoothing through the Gaussian function of the input. So we can imagine this receptive profile acting by convolution as differential operator, in this case of degree 2, acting on the smoothing of the input, retinal input. Here, simple image of neurophysiological measurement of the different receptive profiles in different cells that fits the model of that we have of Laplacian of a Gaussian function and directional derivative of a Gaussian function. Here I introduce this heterogeneous operator that we call L lambda. Okay, what we have here is that two coefficients, A1, A2, and two kind of operators, a Laplacian and a directional derivative of degree 2. I want to stress that here we have heterogeneity in the dynamics of the operators, in the orientation map, and this heterogeneity is put out by the different coefficients. So we can imagine to have coefficient changing point to point. We can imagine to have orientation changing from point to point, and also I will work with this kind of operator most of the talk, but we can also introduce operator of a different degree. So this is the general form of the heterogeneous operator that we are going to consider. And orientation map is pretty known, but I want to stress this. The orientation maps models the distinguished orientation that every cell of the cortex recognize. And in rodents, we have essentially the distribution of the orientation is a noise function. While in primates, we have the so-called pinwheel structure. We will come back to a possible model for this pinwheel structure. Here we have an image right now that may make you understand approximately what is this more not random distribution that we have in primates. So what we mean by heterogeneous Poisson equation is a differential equation where we use this L lambda operator that I introduced just before. On the right we have the action of the operator on the retinal input, and on the left we have the unknown function that is the solution, will be the solution of a reconstruction problem. So if we think back to the operator that I introduced 2 slides before, and we consider a1 equal 1 and the other coefficient a2, a3 equal to 0, we recall the usual Laplacian, and so this is the classic Poisson's equation. Here we are calling this heterogeneous Poisson's equation because we are considering not the Laplacian but an heterogeneous differential operator. I want to stress that while on the right the differential operator models the action of the receptive profiles on the retinal input, on the left this, in our intention, is another kind of, the differential operator models another kind of procedure which is kind the inverse of a reconstruction procedure. So in our intending of this equation, the solution of this problem is a reconstruction operation that is carried on by the cortical connectivity. So the differential operator on the left represents the inverse action of the cortical connectivity, while on the right it represents the action of the receptive profiles. So now, from now on, I'm going to show some reconstruction made through this heterogeneous Poisson's equation, but first I have to say that we use steepest descent in order to solve this equation, and in fact in our work we prove that the solution of the equation above, so this steepest descent, exists with opportune regularity conditions, and it will converge with the time tending to infinity to the heterogeneous Poisson's equation, to a solution of the heterogeneous Poisson's equation, meaning that if we make the time tending to infinity we obtain a function which is effectively a solution of the Poisson's equation, which we can see exactly below in this slide. So let's go on with some implementation. Here I wanted to show just a first a simple action when we consider two orientation 0 and p half, so horizontal and vertical, just derivative of order 2, and so a lambda in this case is a2 equal 1, the other two coefficients equal to 0, and theta, which can be 0 or p half. And from now on I have some reconstruction. So in the left we have this picture of a painting of Piero della Francesca. In the center we have a representation of the receptive profiles in a subsampled set of points, and on the right we have the reconstructed image. In this case this is essentially a Retinex model, so a1 equal 1, a2 equal 0, and our operators is just the Laplacian. In this case we have just the directional derivative of order 2, but with fixed angle, and I don't know if it is clear with this light, but the reconstruction around the face and the blues of the girl in the painting is not so well. Qualitatively you can see that there are lines, the reconstruction is not perfect. But already if we start putting two orientation distribute with random distribution on the image, we obtain a pretty good reconstruction, and the things goes better and better if we consider more elaborated heterogeneous operators. In this case, for example, we have the coefficients, are 1, 0, 0 with distribution with the equidistribution over the image. So in some point we have a Laplacian, in some point a directional derivative of order 2, and in some point directional derivative of order 3, and we have still a pretty good reconstruction. And finally we made a reconstruction with the model of the pinwheel distribution. So in this case we have only directional derivatives of order 2 and 4, and this function down there that models the orientation or a distribution of the orientation is usually used to model the pinwheels distribution. And I also have some reconstruction and some comparison with other models. These on the on the left we have the original image. Center left and center right are the reconstruction through the Kimmel model. Is a Retinex model that have 4 parameters, and on the right our reconstruction. And I want to stress we have the pinwheel distribution, but we have no parameters. So we chose just the distribution, and we have no parameter to choose. So it's a starting project, but it's going pretty well, we think. And here we have again another image in the center, Morel model, and which is again a kind of a Retinex with 1 parameter, and on the right our reconstruction through the same pinwheel distribution and the same heterogeneous Poisson's equation. Now, now I want to stress why we think this model is working pretty well and is so promising. We go into the discrete setting. So this is the notation I will use. Lambda is a finite set in this integer lattice and is symmetric with respect to 0. We denote by x epsilon z the difference operator of the difference operator, the user difference operator. Epsilon is clearly a positive integer, and q is a bounded domain. Q epsilon is the discretization of the same bounded domain. So we can introduce a discrete differential problem in this setting. I think it's pretty intuitive what I'm doing. I'm simply introducing a simplified version of the heterogeneous differential operator in divergence form, and I'm considering this kind of Dirichlet problem. And now I'm going to introduce a notion of homogenization that it's not mine. It was introduced by Kozlov in a paper in the 80s. So we have the discrete setting above that I introduced in the slide before, but in this case the matrix of the coefficient is diagonal, so it is simplified. And below we have a classic Dirichlet problem with again a diagonal matrix of the coefficients, and the notion introduced by Kozlov is the following. So we have H convergence, or H convergence if we make the functions f epsilon tend to f0, and we have that the solution tends to the classic solution, and the first the vector of derivative tends to the vector of derivative of the classic solution in the opportune spaces, that it's all well defined. And we call in this case H0 the homogenization of the sequence A epsilon. Again, epsilon is a factor that tends to 0 in our intention. I forgot to write it on the slide, I'm sorry. And the interesting result is that if we have these conditions on the coefficients, which means, so we have that the coefficients around some point have to have some 1, and they have to be all greater or equal to some positive real number delta. And the last is a technical condition that I'm not going to explain in details right now. Well, if these conditions are respected, we have this important theorem, that is that there exists a homogenization of this sequence of discrete Dirichlet problem, and in fact this homogenization corresponds to a classic Laplacian. So is not only diagonal but is a multiple of the identity, so the homogenization is a multiple of the classic Laplacian. And I want to stress that this is not exactly the problem we started from. It's a simplified version, but it is very promising. In particular, what is different is that we impose this condition in that the coefficients along the coordinate axis have to be greater or equal than delta, so we cannot have operators that are totally degenerate in no point, but we are nearby, we are going nearby degenerate coefficients, and so this is pretty promising, we think. Sorry, this is the result, and I concluded my presentation.
Thank you very much for your very inspiring talk. So it's the first time I see differential calculus done in with heterogeneous operators, then at least in a real application. I mean, not in a theoretical framework, but in a real application. Then I'm really interested in. There are questions from the audience. Yeah, the Remco.
So you added also this fourth order term to the seventh order, second order, fourth order term, and per position this can change.
Yeah.
So with the addition of the fourth order term, I know that inpainting can be done with biharmonic. So I know that inpainting can be done also with bi-Laplacian. But I wonder, is it the kernels, they are no longer strictly, if you look at when the coefficients are constant, and then you would have, then it's a left invariant operator, and so then the kernels are no longer positive, I guess. Is this a problem or not? So why do you add this fourth order term? Why is it important for the inpainting?
We added the fourth term because it behaves well in the reconstruction, but in fact we don't have a homogenization result for the fourth order term. So I mean, the fourth order term is kind of in a strange situation because we can't treat this with the same tools, so we are searching if there are discrete tools that works for the fourth order term, because in the continuous case, in the implementation, the fourth order works well, but we don't have, from my point of view, a real understanding why it is. So I wanted to put the result, but still, you're right that in the homogenization case, this behavior is not clear yet, but still the convergence result is still true. So the convergence result of the steepest descent works well. This is pretty clear.
Yeah.
Thank you for the talk. I really like the design of the slide. So my question is, maybe a naive one. Can you go back to the slide heterogeneous Poisson's equation? I didn't quite understand. So the operator L, is it the same on the left and the right?
Yeah. The operator is exactly the same. What I wrote here, I'm sorry if it's not clear, is that we give a different interpretation of what is going on, because we want to stress that the cortical layers not only register the image, but they reconstruct it. So there is a cortical reconstruction of the image, and this is we can see this on the left, because on the right this is just a function, which once you have the input, the action of the recent profiles give you an output, which is the function. But on the left, this operator, and you have to solve a differential problem, and so the operator on the left, in our intention, is the inverse action of the cortical connectivity, because in fact the action of the cortical connectivity is the green function, so the fundamental function of this operator.
So why if the operator is the same, I is not equal to u? So why u is a Retinx version of the initial function? Because there exists a set of function which is annulled by this operator. So as in the Retinx model, we have harmonic. We reconstruct the original image up to harmonic function. We have the harmonic version of the harmonic kind of functions for the heterogeneous differential operator, and we have the reconstruction is made up to one of these functions.
So just to check if I understood correctly, I is assigned And the U is the unknown, or vice versa? So
I is the sign, is the input, and U is the unknown, and the solution of this problem will be the perceived image.
Other questions? Yeah.
So yeah, we need to, you already mentioned that, we need to avert this, and we have a kind of a resolvent operator that has to be applied. And so do you have some bound, or do you investigate say coercivity bounds for the operator L delta? You say that you have like, what you already said, well, you have a convergence result, but how stable is the operator? Just if you look at the operator.
No, I'm not able to respond this right now. No, not yet. No, not yet.
Okay, so the classical neurogeometrical model for the primary visual cortex is the one of Petitot, Cittisarti, and so on, where there is a fiber bundle. A fiber bundle, meaning that for every point we have a fiber of orientation, and is a three-dimensional space equipped with the group, and so on and so on. And it seems that here you are destroying everything. I mean, with us also, because we are co-authors also. But it seems really that, so you are destroying everything, or you can find, so now you are working not anymore in a fiber bundle, equipped with the Sub-Riemannian structure. That's the classical neurogeometrical model, but back in the two-dimensional plane of the cortex. That's the main idea. Do you think that you are destroying the fiber bundle, or still you can recover the fiber bundle in some way?
I think the cyber bundle is in some way hidden in in the orientation map. I think that this will be the point, that the fiber bundle is in some way hidden in the way we model the orientation map, and the fact that we have to understand why some distribution of the orientation map works better than other. And so I think that once we understand this, we will come back to we will understand what is the link with the bundle structure.
Okay. Okay, if there are no questions, thank you very much to the speaker again.